Expressions. If you've been following along in this series so far and writing code, you've already been using expressions. All of these are expressions, but you're used to seeing them beside an equal sign, where the result of the expression ends up inside the variable. The expression part is only the stuff on the right side. Whenever I've been popping up this aqua box, I've been showing you how C takes your expressions and starts resolving things down in chunks to a final answer. These kind of expressions boil down to a single number. An integer, if everything is an integer, or if you change any part of it to a floating point number, it'll end up as a floating point number instead. You've also been using another type of expression, a boolean expression. The boolean expressions you've been using contains things like doesn't equal or the greater than sign. We've been using them to control the flow of our if statements and while loops, but let's just focus on the expression for a moment. These are boolean expressions because they resolve to something we consider to be true or false. Like how we can express more complicated math by tacking on more operators to our expressions, we can also express more complex logic in our true-false expressions. These different symbols map to 3 different Boolean tools, and we'll get to each of these soon. But first, like always, we have a problem to solve. A friend from school is doing some research on concert volume. They sent volunteers to a few concerts with decibel meters to save a reading every 60 seconds. Those readings were combined into a spreadsheet for each concert like this. The first column is time, in seconds, starting at 0. And then there's 3 columns for each reading at 3 different positions. One person stood at the front of the stage, and another in the center of the floor near the sound engineers, and the last near the back wall. So these 3 readings correspond to the decibel readings at that time in these positions. Your friend compiled 50 different spreadsheets like this, and she wants your help to flag concerts that meet any of the following criteria. First, what's the longest period that we are continuously above 100 decibels in all 3 zones? The louder the music, the shorter the time before damage to your hearing can occur. We want to know if the longest we stay above 100 decibels is greater than 15 minutes, because that amount of time can cause hearing damage. Second, we want to know if we ever hit the critical volume of 120 decibels in any of the 3 zones. 120 decibels is about the same as a jet engine takeoff, and it can only take less than 10 seconds to cause damage. So we just want to flag any concert where this occurs. And third, we expect that the quietest place in the concert should be at the back of the room furthest from the speakers. But sometimes, counterintuitively, that's not always the case. Some venues have acoustics where sounds bouncing off walls can become amplified. So we want to count the number of times where the back reading is not the lowest reading. Let's start by reading in our data. There's a ton of numbers here, so how can we approach this? We need to break down the data into some reasonable chunk. Since our data is already segmented into rows, with each row corresponding to 1 time, it seems natural to try to process 1 row at a time. If we were to read in 1 line of data, it would look like this. We'll read in an integer for the time, and 3 doubles for each decibel reading. So that's 1 row, but we need to repeat this again and again for each row. That means we need a loop around our code here. And we just need to figure out how many times we need to loop. Luckily, it seems that every spreadsheet has exactly 240 rows, corresponding to 4 hours of data. So we can simply count up to 240. Now our program should read all of our data in. Let's quickly verify that by printing out what we've read and running our program. Great, and now you just need to start typing all 960 numbers into the program. Just kidding, computers are supposed to make things easier for us. So let's figure out a way for the computer to do this for us. Most spreadsheet programs will let us save a copy of a spreadsheet as a tab-separated value file. If you want to follow along, I'll put a link to this TSV file in the description. This file is just a text file, kind of like our code files, and we can open it in our text editor. You'll see it's just all of the data from the spreadsheet, but with tabs separating each column. What's nice about tabs is they're completely ignored by scanf. If we put the TSV file inside the same folder as our program, we can ask the computer to feed our file into our program by using this little angle bracket and the name of the file. Now, instead of us needing to type stuff into scanf, the computer is typing the file into the program for us. We don't see the input being typed in, it's happening under the hood, but we see all of our data being printed back out to us from our printfs. Great, so now we just need to analyze our data to answer the 3 questions from before. Our first one is we want to know how long we are continuously above 100 decibels in all 3 zones. Near the beginning of our concert spreadsheet, you can see that we're hovering around 100 decibels here, in all 3 zones, for 4 rows. So we consider this to be above our threshold for 4 minutes. Notice that these neighboring rows also have a few values above 100. But we don't want to consider these as part of our loud section because not all of the readings are above 100 decibels. These ones are only 90-something. We need to detect these relevant rows. To start simple, let's just focus on one column to begin with. If we wanted to find the rows where our first column, our closest stage reading, is above 100 decibels, we already know how to do this. We'll create an if statement and check that the column is 100 decibels or above like this. As the program runs through, it'll print out just the rows where that first column hits 100 decibels, and ignore the values from the other columns. Now let's bring in our other column. If we're inside our if statement, we know that the first column hit 100. So if we also check that our second column is also above 100, then we'll only get here if both are above our 100 threshold. Whenever we hit a row where the first column is at or above 100, we'll also check if the second column is too. But because the second column isn't, we'll skip over our printf. And if we get to a row like this one, where the first column is below 100, we'll skip over everything. Only if both conditions are true will we enter both if statements and print out our data. It's super common that we need multiple conditions like this to be true. So basically, every language lets us combine our 2 if statements into one. We'll take our condition from the second and move it to the first, combining it using AND. These 2 ampersands stand for AND. This now reads, if stage dB is greater or equal to 100 and center dB is greater or equal to 100, then we'll print out the time. AND requires that both conditions beside it are true. This does the same thing as before. When the program reads our first line, it'll check that our stage is above 100. It is, so that part of the expression is true. Our AND then needs to check if the center dB is also above 100, which it's not for this row. That's false. Since both sides aren't true, AND makes the whole thing false, and we won't print out anything. On the second row, our stage didn't even hit 100, so that part is false. Technically, the second part, for the center dB, would be true. But it doesn't matter, since the first part is false, and already has enough information to decide that the entire thing is false, and again we skip. Same with the next 4 lines. All are entirely below 100. So each of them will have a false condition and we'll skip printing. Only when we get to these lines do things change. Since both are above 100, our AND is finally happy. It'll resolve to true and we'll get our rows printed. Exact same behavior as before, but much more concise code. For our third column, we can also add on that condition with another AND. So now we'll enter our if statement if StageDB hit 100, and CenterDB hit 100, and BackDB hit 100. Now all three subconditions must be true for the whole condition to be true. You might notice that even though we've chained all three conditions together using ANDs, C still treats them separately. It'll process one of the ANDs first, then feed that result into the last AND. Ultimately, AND only cares about its direct left and right side. So another way of thinking about this is that C extracts a smaller chunk out, figures out that part, and then feeds that into the next part. Or you can ignore all of this and just kind of think about it as an English statement. Now that we've flagged the right rows, we need to figure out how long we stay above that threshold. Specifically, we need to know when we get to the first row in a section that we've hit our threshold. So that way we can remember that time as the start time. Then we'll keep checking later rows to see if they're still above the threshold. And we'll calculate the amount of time that passed between that row and the start time. If that time is greater than the longest we've seen so far, we'll save it in another variable, which contains our top result. We'll repeat this process for each row. You'll see that once we get to this longer section, we'll keep updating our max time. This should work, so let's implement it. I'll start by creating an inLoudSection variable, which will track whether we're currently inside a 100 decibel section. It'll start at 0 to represent that we're not in a loud section yet. And once we've hit that threshold, determined by our if statement, I'll set that variable to 1. But we only need to do that whenever it's currently 0. If it's 0, we know that we've hit the first row in a section, and we should save our start time. After the first row, our flag variable is already set to 1, and we won't enter this if statement anymore for this section. Then we'll calculate the length of the section so far by taking the current time and subtracting the start time. For the first row, the current time is the same as the start time, resulting in this saying that we're above 100 decibels for 0 seconds, which isn't very helpful or representative. Let's assume that our reading applies for the whole minute. That means I'll add 60 seconds to our calculation. Once we have our time, we'll store it in a max time above 100 variable if it's greater than the current value in there. We just need to make sure that we reset our isInSection variable back to 0 whenever we leave the section. Otherwise, our program will keep using the first start time it finds for the whole program. Lastly, since our goal is to find if we're louder than 100 decibels for 15 consecutive minutes, I'll add a check after we're done processing all of our data. If we're greater than 15 minutes, our program will say that we exceeded our safety window and for how long. Awesome. This should complete our first goal. Let's see if this concert hits our critical threshold. And off we go. The program basically does nothing until we get to a row where all three readings reach 100 decibels. When we do, things get more interesting. We'll check if our isLoudSection is 0, meaning that this is the first row in the section. Because it is, we'll set our flag to 1, and then save our time into our start time variable, which we'll use to calculate our length of time in the section so far. And then check if that time is greater than the highest we've seen so far. Since this is our first relevant row ever, it's definitely our biggest, so we save it in our max time above 100. For our second row, since we've set the inLoudSection to 1, we won't resave our start time. Meaning when we calculate the time range, we'll get a bigger number than before, which we'll save. So we leave this section with 120 seconds stored in our max time variable. The next row is below the threshold, so we reset our in loud section back to 0. And we begin our search again for the next section. This row hits it, but since it's only 1 minute long, we won't change our max. And we continue on like this. This section goes on for 4 minutes, so our max variable will get bumped up to 240 seconds. We zoom along until we get to a very long section, which you'll see updates our max time several times. Actually, that's the longest range for this concert, and while we'll process other rows, none of them will break our record. Then we get all the way to the end and finally leave our loop. We now check if we were above 100 decibels consecutively for 15 minutes. And since we were, our program prints out a single warning message. I'd probably wear earplugs for this one. Our next goal is a bit simpler. We need to simply flag the rows that contain any reading of 120 decibels. And let us check if multiple things are all true, or lets you check if at least one condition is true. As you know, to check if one column hit 120, we do this. If stage dB is greater or equal than 120, we'll print out our critical volume hit. We can add a second condition using OR like this. This reads if stage dB is greater or equal to 120, or if center dB is greater or equal to 120, then print out our critical volume warning. OR is represented by these two pipe characters, which you might have never noticed before. On a standard US keyboard, it's the same key as the backslash above the enter key. You just need to hold Shift and hit it. With OR, as long as one side is true, the OR will be true. So when we run our program, once we get to this row, it'll enter our if statement since the first column is above 120, even though the second column isn't. This row will also be true. The stage column isn't above 120, so that part is false. So C will also check if the center column is above 120. Since we got one true, the whole thing is true. And of course, if both are true, then the OR is also true. We just need to tack on the third column, and all of our correct rows will get detected. This works, but we get a lot of redundant messages for each critical row. The ask from our friend was to simply flag the whole spreadsheet, so we really only want to see the message once. To track whether we've hit the critical volume already, I can create a new hit critical variable and set it to 1 when we've hit a critical row. We want to print the message if any row is above 120, but only if the hit critical variable was never set to 1, meaning if hit critical doesn't equal 1, and if any of our readings are above 120, then we'll print the message and set the flag to 1. Now when our program gets to our if statement, it checks that hit critical isn't 1, which is true. And then it needs to figure out if everything inside the brackets is true. It kind of separates that stuff out and figures out what that ends up as. For the first row, it'll end up being false since everything is below 120. Then that false is fed back into the AND, and since both sides aren't true, it's false and we don't enter the if statement. And the same happens for these rows. Until we get all the way to the first one that has a value of 120. When we get to such a row, our hit critical is still not 1, but the inner part of our brackets will become true, which is fed back into our AND, which makes everything true. So we'll print out our message and set our variable to 1, which means that for every other row, we won't enter our if statement since the first part of our AND is always false, even in the cases where the second part would be true. These parentheses are very important. Just like how in math multiplication comes before addition, there's also an order to how OR and AND interact. Without the parentheses, our if statement asks a different question. It only applies our AND in between the hit critical and stage DB only. Then it checks the other two readings independently, meaning only the stage decibel reading can trigger the print once, but the center and back will trigger the message every time. The reason is because of the order of operations, which is defined that AND comes before OR. Honestly, I had to look that up since it's not something you really need to know. Whenever you mix and match them together like this, basically everyone just puts parentheses explicitly in the expression so that it's obvious. Okay, we're almost done with our 3 favors. And for our third and final goal, we're going to use our third and final Boolean tool, not. OR and AND combine 2 Boolean expressions. Not, on the other hand, inverses an expression. It flips true to false and false to true. We want to know when it is not true that the reading near the back is the lowest. This condition describes when the back reading is the lowest, when it's lower than the stage and the center. If we wrap it in parentheses and put an exclamation mark in front of it, we'll get the opposite. You'd read this as if it's not true that back dB is less than stage dB and back dB is less than center dB. Then we want to keep a count of the number of times this happens. And we'll print out the total at the end if it happened at least once. As we run through, you'll see that whenever we hit a case where the back is the quietest, the inner part of our expression is true. But our non makes it false, so we don't do anything. But when we hit the case that we care about, the not flips the false to true, so we enter and increase our count. Using not is a bit of a matter of style. We can express this condition this way, or we can reverse everything and it does the same thing. It really depends on what you think feels natural for what you're trying to express. If you describe the condition to another person as when this doesn't happen, then you probably want to use not. I'd say, don't think about it too much and it'll become obvious to you over time. Now with our 3 new powers, we have a full program that we can feed in the different spreadsheets for the different concerts and get different results. In these last few videos, we wrote a bunch of code from scratch, but it's also an important skill to learn how to read and modify code. You do a lot more of that in the real world than starting new. For this video's experiments on codeaesthetic.io, I have 3 programs for you that mostly work, but you'll need to expand them using your newfound powers of expression.